Good morning. This is Larry Olson with Olson Engineering and Olson Instruments, speaking to you from Wheat Ridge, Colorado, our corporate office. We also have a branch office in Rockville, Maryland. I want to thank everyone for attending our webinar today. We're going to be talking about interferometric phase radar and its applications on bridges, their stay cables of bridges, and also on wind turbines. So for those of you who are attending the webinar for the first time, this webinar will be posted, as it says in the chat room, in about a week or less, up on our website under services, under training and webinars. We've done about 5 or 6 previous webinars that are also posted up there that you can get a downloadable link to and view on YouTube videos. So without too much further ado, today's talk will be presented by myself and our Senior Engineer NDE Project Manager, Pat.miller, who will be doing the second half of the presentation. So I'll start it today and then Pat will take over in the middle. You can use the chat room at any time if you have any questions or problems. Our principal geophysicist, Dr. Ryan North, is co-hosting the meeting and he's running that side of it at this time. So at the end, you'll have an opportunity to ask questions through the chat room and we'll respond to those. So thanks again, and without too much further ado, we'll get started today. Okay, I already mentioned the first slide. We're going to talk about radar monitoring. So this IBIS system, or imaging by interferometric survey, as it says here, is manufactured by IDS Georadar in Pisa, Italy, and they have an office in Golden, Colorado, quite close to our firm. So it is a ground-based microwave interferometric system, radar, that works with remote precision measurement of displacements and vibrations of structures. There's 2 versions. One is for static monitoring of landslides, dams, and slopes that goes back and forth on a track. Can be a topic of another talk another day. But that gives you static monitoring. About every 5-minute typical cycle time, it will go back and forth 2 meters and very precisely measure within 0.004 of an inch the movement of slopes, dams, and other large features. Today we're going to be focused on the IBIS-S for structures. Its system is the same electronics and antennas. These are the antennas shown here. Runs into a notebook in the field, battery powered, set it up very quickly on a tripod, and focus it on the bridge or structure. It is a step frequency radar that goes from 17.1 to 17.3 gigahertz. It uses synthetic aperture radar to locate where the landslides and slope specifically are moving, because it's static in that case by going back and forth. But in this case, we are focused on the structure. So what is interferometric radar analysis? Basically, it's the idea of projecting these high frequency radar waves with wavelengths on the order of 19 millimeters or 3/4 of an inch for that frequency range in the US of 17.1 to 17.3 gigahertz. So as you can see in the acquisition below, as the antenna sends out the signal, you're looking for the change in phase of the reflected radar signal. And from one sampling interval to the next, you're looking at this change in phase, and the displacement during that time is equal to the wavelength of the radar divided by 4 pi times the change in phase. Now it actually is fairly complex in that it does 16,000 to 32,000 steps of frequency very rapidly. As I think about the advancement in technology, both in electronics, computational power, it's incredible what's occurred in my career, because I went from graduate school at the University of Texas at Austin under Dr. Ken Stokey, working on some seismic measurements using an old oscilloscope with a Polaroid camera, and my fellow PhD graduate students got the first HP digital dynamic signal analyzer back in 1978. So it's greatly advanced since that time. Electronics allow amazing measurements. So here's an example of what you do with it. You are sitting at a point here. The radar is reflecting, say, from a crossbeam of the bridge. That line of sight reflection with trigonometry is turned into a vertical displacement. If it was a building, you would use trigonometry to turn it into a horizontal displacement. But that's, and generally you want to see at least 10 to 1, 10 horizontally to 1 vertically, ideally 5 to 1 for better accuracy or greater angle to get the best vertical displacement on a bridge. So the static landslide system, because it tracks back and forth, can determine where the reflectors are coming from. Because the IBIS-S for structures has a dynamic response as well, up to 100 hertz. You do not get that opportunity. Instead, you have to identify what the reflectors that you're seeing every 0.75 meters along the way. So it's very important to know what your reflectors are. You can use different horn antennas for different angles of coverage as you project the radar. You can have a narrow beam radar in a simple sense to a wide beam radar. From nominally 15 degrees angles plus or minus to 70-degree field of view. I included this from some work that IDS did early on to prove the accuracy of the IBIS system versus a total station. So they've established that it's accurate to 0.004 inches or 4/10,000ths of an inch, which is 100th of a millimeter. So they set up a target to reflect the radar energy, focus the IBIS and the total station at it, and did a series of steps. There were 3 1 millimeter steps, a couple of 0.5 millimeter steps, 5/10 of a millimeter steps, as compared with the total station. So the IBIS-S results are shown on the left for the 1 millimeter steps. You can see it's very precisely measuring the 1 millimeter steps as done with this micrometer that was moving the target. And these little spikes are actually when they touched it to move it. So it's a very sensitive system. The total station results, of course, agree. They're shown there as well. The 0.5 millimeter steps also showing the same effect and the same correlation. So it's amazing precision that you get out of this high frequency radar with the interferometric approach. So what are some of the advantages? You can carry out a survey without accessing the pressure structure. In other words, you just have to be able to see it and focus on your targets. You get an area from the information out of the whole area that you're covered by the antenna. And there's high accuracy, as already mentioned, to 4/10,000ths of an inch. You can do that statically out to 1,000 meters with the proper angles of ideally 5:1 to achieve that accuracy, or steeper. The dynamic vibration response is up to 100 hertz when you're close, and as high as 40 hertz, which is very good for both bridges and other structures. It easily covers the range at 500 meters. So it's a very precise system, both dynamically and statically. You can run it even in bad weather. You can run it without human intervention, taking the data. And the acquisition frequency is just the order of seconds for the IBIS system. So the first case history that we got involved in, we did it with Lorenzo Mayer of IDS in Pisa, Italy, Dr. Bojadaryanov, a New York City DOT engineer in charge of their structures and maintaining them. Myself and Dr. Andrew Smythe with Columbia University. We wrote about this in a TRB paper. Dr. Smythe at Columbia had done earlier GPS work on the Manhattan Bridge, and that's what's shown here. We set up the IBIS system on the Brooklyn side of the bridge. That's actually the Brooklyn Bridge in the background, looking towards downtown Manhattan on the other side. So we're sitting here on the bank, looking across and down the center of the bridge, and also on the edge ultimately. So some background information on the Manhattan Bridge. It's a suspension bridge with the truss frames underneath, as you might have noticed. It's a fairly long span. There's all these cables. We set up the IBIS-S on the Brooklyn side, looking back through this pier or on the edge along this cantilever stretch from below it. This just shows another view looking north. And basically, we were set up over here to the right, looking across, and we got out to about 356 meters, basically beyond midspan of the bridge, because it's as far as we could see from that access point. You can see it's well used. There are a variety of traffic lanes for vehicles, trucks, and cars, and there are 4 subway train lanes. Well, the bridge was a subject of some concern because in high winds and rain and other things, and depending on the loading of the trains, which are by far the heaviest load, it could twist up to 9 feet over that 115-foot length side to side. And that kind of torsional twisting at midspan was of definite concern to the city of New York, to Dr. Yanoff and others. So to address that concern, they invested almost $1 billion over about a 10-year period to stiffen the bridge by using torque tubes. So they stiffened underneath with these X-out torque tubes. And they monitored it, and that's where Dr. Smythe was involved over a period of months with GPS receivers to see if the stiffening had resulted in the desired reduction in torsional twisting. And indeed it had. These are some GPS results showing that under this loading, every so often over this time frame in seconds, there would be a train, and the train would move at nominally 300 millimeters or a foot at this particular midspan location. And the Brooklyn-bound outer roadway edge versus the Manhattan edge was similar, but the trains were moving it close to 300 millimeters or a foot as they went by. And you could have from 1 to 4 trains on the bridge at a time. So this is a view of where we were setting up. We were literally looking down the center of the pier, and these were excellent targets. These are very large, deep steel beams. They're spaced every 5.5 meters apart across the bridge as part of the truss system underneath. And so we were able to survey that very well because they were good natural reflectors. This radar reflects very strongly, as you can probably appreciate, from steel. Just like structural radar is very good at finding reinforcement and mapping it out in a 2D and 3D fashion. We also, because of interest, and we did all this work in a half day where the study by Columbia had been done over several months, we went out to the edge for the second part of that half day for a couple hours and monitored these cantilevers, which were the extension of the cross beams, to see how much it was twisting in a global sense, maximum twist or maximum displacement, I should say, relative to the center. So this just shows how many reflectors we could see. This is what's called a bin range power plot of what are the strong reflecting targets. And as highlighted in color here, they were those big cross beams. And right down the center, carefully sighted, we could see out as far as we could see to where visually you can't really distinguish the cross beams, the radar could. And this is showing going from nominally 46 meters to 356 meters. And every one of these peaks that have more amplitude in the signal to noise ratio are those beams that are reflecting. So basically we were seeing about 60 beams in one measurement, in one setting, because the radar is able to discretize the data as long as the points are more than 0.75 meters apart, and the beams were 5.5 meters apart, so they stood out very well. And there's just a zoom here showing those power, the signal to noise ratio of those reflections from the beams here. So this is a result over a half-hour period of monitoring, and it's the midspan result. So we have many results from the other beams, but this is the midspan beam, the cross beam. And you can see deflections nominally 300 to 350 millimeters, nominally a foot to 14 inches as you go across. As every train went by is when it moved the most. So the number of trains crossed during that time going into and out of Manhattan and between Brooklyn. So this is an expanded view of the same data of one of the passages, a 4-minute view showing as the train approaches midspan, you start to really move it. It deflected 300 millimeters, and then it came back. That time was not so long, less than a couple minutes to pass by the center of the midspan and move on. So this is the plot that I think starts to give you an appreciation of the power of the system, because we're seeing 60 measurement points, meaning 60 beam responses are all overlaid on each other in this plot of, again, a half-hour of data. So it's a lot of data. You can discretize it and look at specific points along the way and end up plotting the bridge deflections. This shows that maximum deflections that were measured in peak-to-peak vertical deflections in millimeters of the center of the beam deflections, right down the center of it, versus the outside northern edge deflection on the cantilever part, as I mentioned earlier. So earlier, this twist in the extreme was getting up to 9 feet that it was moving, 2.7 meters. Now you can see during our monitoring time, which wasn't excessive wind or anything like that, it was actually pretty good weather, but you can see how as the distance gets down the main span to midspan here and back again, looking out to 356 meters, how we're seeing very little difference. 500 millimeter maximum displacements at midspan on the center deflections versus about 550 millimeters. Only a couple inches more deflection on the edge based on the loading of the outside trains. So in any case, it showed there was very little twisting going on anymore. It was the torque tube system really did stiffen the bridge. And this was all achieved in a half day of monitoring. We also looked at some background vibrations when it was just traffic and no trains. And from this, you can get the natural frequencies of the bridges just by being excited by wind or the traffic, truck traffic in particular. So this just shows it's a much lower displacements, less than plus or minus 40 millimeters, and just some drift and things moving during this time. But that's not very much displacement. So when you do the fast Fourier transform to look at the FFTs, if you will, or frequency content, there were three main resonances that showed up even in that data. You can do this for modal vibration testing too by looking at multiple points in a line. But those frequencies were quite low because it's quite a large bridge, 0.23 hertz, 0.3 hertz, and 0.49 hertz, where this is 0 to 3.5 hertz on the FFT. So the second case history I'm going to talk about was sponsored by the Federal Highway Administration through Parsons Brinckerhoff, now WSP, and I'll give some certainly credit to them for inviting us to be part of the project. The primary focus was a conventional load test done by Drexel University on the bridge, but they were also evaluating other technologies. And we ended up demonstrating it over a couple-day period on the span 2 southbound, which was a focus of the load testing as well. They monitored multiple girders. We looked at girder 3 specifically to compare with their results. So this bridge is a conventional steel girder bridge. Looking underneath it, we decided there was so much steel present, including a metal deck, that we decided not to think we could see the diaphragms. We could, as it turns out, that went across. But we attached, as you'll see better in the next presentation that Pat Miller will deliver, corner reflectors, which are basically hard to see right here, but they're a metal reflector, and we mounted them right at the location on the other side of this girder, number 3, where Drexel had mounted their string potentiometer monitoring system. So we're shining, you can see the unit shining up. These are relatively narrowly focused 15-degree plus or minus sending antennas. You can change these easily to be a field of view up to 70 degrees as needed. And this is a receiving antenna. So it's sending and receiving from the IBIS unit. So Drexel had arranged for load testing. They had put their, in this particular span, 2 and 1, we're focused on span 2 here on the southbound side. You can see it's a skew to the bridge in terms of the pier, but the southbound traffic, they had string potentiometers at each of these asterisk starred positions that are shown. Ultimately, and the most load applied was from 6 loaded dump trucks weighing a total of 460 kips that were pulled out and positioned over each of these spans, referred to as 3/4 of the span, half span, or mid span roughly, over the mounting points, and quarter span as it was further south. So we had reflectors set right at this position on girder 3, the mid-span position, and the quarter span position as well. Shown to the right is the system used by Drexel with a displacement sensor that had a string going down to the ground with a heavy weight to show the movement as the load trucks went by. That was a string potentiometer system to do that. So the results of the IBIS system done over this 1-hour loading period, and we actually checked many times with different loads during the load testing, but the real focus was on this, where you can see the receiver 1 is at the quarter span, receiver 2 is at mid span, and receiver 3 is at the 3/4 span, or the north end. So these are the deflections that are shown. You can see that the loading at mid span, when the trucks were right over it, definitely resulted in the most deflection, about 0.85 inches. You'll see that precisely in a minute. At mid span, out of receiver 2. The loading at 3/4 span had the most deflection, about 14.7 millimeters. It's shown on the screen, versus the midspan deflecting about 14.2 when the loading was a 3/4 span. And a little bit surprisingly, but due to the skew of the bridge and other reasons, the stiffness was such that the greatest deflection when it was at 1/4 span actually happened not at, as you would have guessed, the receiver right below it, which went 12.8 millimeters. It happened at the midspan, which had a 14.8 millimeter deflection. So this table compares the results of the maximum displacements measured by the IBIS-S for loadings at the 3/4 span, the north end, the half span or midspan, the center, and the 1/4 span at the south. So the maximum displacements measured by the IBIS are shown versus the potentiometer maximum displacements. They agreed very well within from 0.01 inches to 0.05 inches with the potentiometer measurements. So again, this has been proven a number of times by IDS, GeoRadar, and others that it's a very accurate system and agrees well with static traditional measurements. So with that, I'm going to turn it over to Pat Miller to join you now. And I think he'll continue the talk as we speak about a local project here. I'm going to start the video so you can see, at least in the upper right, Pat's face briefly, and he can stop it as he gets going and continue. So thank you, Pat.
Good morning. Thanks for joining our webinar. I'll go over one more bridge to look at, and then we'll talk about a few other applications, including some stay cables and some wind tower monitoring. So I'll jump right in here. First bridge we're going to talk about is a concrete girder bridge here in Colorado. It's very near our office. This was still kind of early on in our learning curve with the IBIS system, so we did have some assistance here from IDS, specifically Lorenzo Mayer of IDS from Italy came over and helped us with the data collection and the data processing. So we definitely want to give him credit as well. As Larry mentioned, because this was a concrete girder bridge, fairly smooth underside, there's not a lot of natural reflection points. So what we needed to do was to add some nice reflectors. So we have these corner reflectors, we call them corner reflectors. They're aluminum, we had them manufactured, and it's kind of like a prism where the radar will shine up in that corner and then bounce back towards the radar unit. So we simply mounted those to the top of the Jersey barrier along the inside of the curving bridge at nominally 7.5 meter intervals. We put 5 reflectors up there on this span, so we could kind of monitor the deflection of that span entirely. Oops, there we go. So there on the top left photo, you see the corner reflectors circled with the colors. The bottom right photo actually shows you a picture of those reflectors from the top of the bridge. We kind of epoxied the base plate of those reflectors on the Jersey barrier. Then we also added a sandbag there just to make sure that we didn't lose any of those reflectors off the bridge. There in the lower middle section, you can see the power profile or the range profile of the reflections. And so you can see that while the concrete bridge has kind of low background, not very distinct peaks, these corner reflectors really stick out and give you really nice reflection points to monitor your data from. We'll look at the displacement time series. This is a plot of displacement. So it's time on the x-axis, vertical displacement in millimeters on the y-axis. And this shows a series of testing trucks. They were doing laps with a semi-truck loaded with concrete barriers as kind of a proof test. And then there's also other vehicle traffic. The bridge was open to normal vehicles as well. And this is showing all 5 of the corner reflectors there. You can see the CR is corner reflector 1 through 5 and the different colors. So again, we're able to monitor all 5 of those reflectors simultaneously and show that displacement data that's occurring. Here's a shorter period of time. This looks like it's about 30 seconds or so of time with displacement. There's a 2.26 millimeter peak-to-peak vertical displacement can be observed when this truck went by. The maximum displacement is near the midspan, those reflectors, with less displacement near the piers. Again, we can do a Fourier transform on that displacement data to look at the natural frequencies of the bridge. This shows those natural frequencies. We kind of picked off 6 peaks here. The first 3 peaks we believe correspond mostly to flexural modes of the bridge, while the latter 3 peaks may be torsional modes or other types of vibrations. You can see that fundamental mode about 1.3 hertz for this fairly stiff box girder concrete bridge. We also want to discuss another application for the IBIS-S, which is to monitor the vibration of stay cables or stay cable bridges. The goals of the monitoring would be to identify the amplitude of the cable vibrations, to identify the natural resonant frequencies and potentially damping factors, and also to evaluate potentially the tension and operating strain of those cables. Again, we're going to show some examples that IDS has put together. Specifically, Carmelo Gintel wrote a paper in 2010 that we have some information here from. Again, we want to give credit to IDS and the people there for putting some of this together. So conventionally, equipment used to monitor stay cables would be accelerometers or laser vibrometers. They each have their limitations. Obviously, with accelerometers, you need to mount that accelerometer to those stay cables. So either you have to go up there and mount those accelerometers and take them down every time you want to monitor them, or you have to have some type of long-term monitoring program where those accelerometers are built into those cables. And that can be a lot of maintenance and data to upkeep on a continuous basis. The laser system can measure a single cable at a time. It's lower accuracy on longer distances, so it can be difficult to monitor large bridges with many cables at greater distances. The advantages of the IBIS-S we get to measure the displacements directly. It's a very accurate measurement, as you've seen from the bridges. Most of the time, you don't need any type of traffic control or shutdown. You can usually monitor from the side of the bridge, maybe the bridge pier or a sidewalk. Most of the time, you can find some spot where you can set up the system to have a good view of the cables and monitor those without the need for traffic control. You also can simultaneously measure a large number of cables. So usually one side or one span of a bridge, you can monitor all the cables of that span on that side at a time. As Larry mentioned, the system's really rapid to set up. So oftentimes we can have the system set up in 15 minutes and we can be taking data. So even within an hour or two, we can get a great deal of data and really have that side of the bridge figured out, move to the other side, and so on. So here's an example from the Olginate bridge in Italy. I'm probably butchering the pronunciation. This is a bridge, obviously, you can see that's kind of under construction, it looks like, while they did the investigation of cables. Again, this was done by IDS. You can see the schematic in the upper right showing the system was set up down near the pier, shining up so that all the cables are at different distances from the system that can be identified. The range profile here showing the reflections of those cables. This would be the nearest cable, cable 2, 3, 4, 5, and 6. And this is the displacement time history of a single cable. So this is over about 15 to 20 minute time period with displacement in millimeters. And you can see they're getting peak to peak displacements of about 2 millimeters during these events, which may be wind gust or some type of loading on the bridge. Again, this bridge, these cable vibration study was compared to accelerometers. It's hard to see in these plots, but what it's showing, there's actually a displacement time history of the accelerometer as well as the radar system, and they're virtually identical. And so this is kind of showing 2 periods of time with both sensors shown on both plots, showing the vibrations match very, very carefully. Again, we can do the Fourier transform on that time domain data to look at the resonant frequencies of those cables. So you do get additional resonant frequencies in the data that are maybe due to the bridge itself. So you kind of have to know, you're mainly looking for these predominant resonant frequencies that are at intervals. And so these red lines show the first 6 resonances of the cable from the IBIS data, as well as the first 3 resonances of the cables from the accelerometer. And this is typical that we've seen, is oftentimes the IBIS data actually gives us, we get more higher modes from the IBIS data than we do from the accelerometers. But again, they compare very well with one another. The table of the resonances is shown down here. Is the lowest resonance being 3.9 hertz, virtually identical between the IBIS and the accelerometer. You can plot those frequencies versus the mode number, so the fundamental mode, second mode, third mode, and so on. They give you a nice straight line. You can also calculate the tension from those resonant frequencies. So for most cables, the tension of that cable is just equal to 4 times rho, where rho is the mass per foot or mass per length of the cable, times the length squared of the cable times the resonant frequency squared. So if this is the fundamental mode, or N is 1, then it's just simply the resonance squared. So here they calculated the tension. They calculated it for each of the modes they observed, and you can see that the tension is identical for each mode, as you'd expect. So as far as the advantages of the IBIS system, oftentimes the personnel that you need to employ the system, with the accelerometers, you may have 3 or 4 people between having a lift to install accelerometers and traffic control and all those extra add-ons you need to accomplish, where the IBIS system can easily be run by a single person or maybe 2 people at max. Number of devices, obviously you need an accelerometer for each cable you want to monitor, where with the laser or the IBIS system, you only need a single unit. Install time, that may take you 30 minutes to install each accelerometer on each cable, where with IBIS, again, you can set it up in 10 to 20 minutes and see that whole array of cables all at once. So the acquisition duration is about the same. So the field activity with the accelerometers, with the install and takedown and traffic control, that may take you multiple days to do a good quality assessment of a large bridge, where with the IBIS system, oftentimes on a single day, we can move around and monitor all the cables on a bridge. Again, there's no need for a lift or a boom truck, and there's often no need for traffic control. So here's a small pedestrian bridge that was done in Denver, with University of Colorado in 2012. Performed this monitoring. He used our system. We trained him on the system for his master's thesis. And so here's a photo of the pedestrian bridge. It's got 3 cables on kind of each side of the span, and there's 2 spans, so a total of 12 cables. The data, again, from this is the Northwest top stay cable. This is the frequency domain data. This is showing the resonant frequency of that cable being 2.4 hertz. And again, you can see that second mode there near 5 hertz. Paul also did a data comparison with accelerometers. You can see that the accelerometers and the IBIS system match very well for each of the 12 cables. This is a photograph showing the accelerometer mounted to a cable. And lastly, we'll go over one other application, which is to look at wind turbine towers. So this is a case study where we looked at the turbine towers with both the IBIS system as well as some strain gauges. So the objective was to measure the tower displacement and the resonant frequencies of the tower with the IBIS system, to measure the tower strain with the strain gauge at the base of the tower and compare those two measurements. We took the data while the turbine was shut down, so it was not spinning actively. And then we took the data in the direction of the predominant wind at the time of the testing. So this was really just the natural frequencies of the tower due to the ambient wind loading. Here's some photos of the setup. The photo on the left, you can see the tiny IBIS system there in the circle on the bottom right of the photo. These are, obviously large wind turbine towers. A photo showing the system pointed up at the tower, kind of a photo from the system's perspective. So the IBIS setup was, we set the system up 12 to 12.5 meters away from the base of the tower. We had the sensor head at about 60-degree angle, and we were looking at the weld joints between the sections of tower. So the bottom tower section was approximately 22, 23 meters tall, and then the middle section of the tower, there was a nice weld joint there that was our primary focus at about that height of 22.5 meters. But there's also additional weld joints throughout the tower at intervals, as you can see there in the photograph. And each of those weld joints actually is a good reflection point, and so we get data from each of those joints. Here's the strain gauge setup. We used an Omega 350 ohm strain gauge. It was mounted 24 inches up from the base of the tower. You can see the close-up view there with a little tape across the tower, so we don't short out the leads there, and the strain gauge is epoxied onto the bare steel. This is, again, a range profile from the IBIS system. So on the top right, you can see each of these little peaks is related to a weld joint on that tower. So in this instance, I've picked off kind of these four peaks to look at, so I can look at these 4 points. Again, you just have to get really good data from multiple points. You can really look at the full action of that tower. So the tower is essentially a bridge, but standing up. So if you think about it as far as the geometry sketch here goes, if we rotate that, then this little red dot here would be our system. We're looking up at it, and we're getting these reflection points from different heights of the tower. Again, we're measuring the displacement toward the unit in this angle, but with some simple trigonometry, we can calculate the projected displacement. So assuming that displacement is completely horizontal. So there is the assumption that the displacement is in a single direction. So again, we try to line up with the tower in the direction on the leeward side of the wind for that day. So we're looking at assuming that displacement is towards us. So here's some time domain data for approximately a 10-minute time period. The top plot is from the IBIS system. This is the reflection there at about 22 meters high on the tower. This is projected displacement in millimeters. It's a maximum of about 6 millimeters peak to peak here early when we had stronger wind, and then it kind of died down a little bit later during the time period. This is the strain gauge time domain data over the same time period. You can see that the two follow each other quite closely, and you can see the same events in the data in both records. The maximum peak to peak strain or micro strain was about 45, again here early in the record, and it was less later in that time period. So looking at the same data over a 1-minute period, again, you can tell they can compare very well. You can see similar features. For instance, this peak is a little less strong, and then with a stronger peak following. So we could really line these up with events in the vibration of the tower and compare that exact same time occurring between the displacement and the microstrain. Doing the Fourier transform, we could look at the resonant frequencies of the tower. Each of the towers we looked at had a very consistent resonant frequency of 0.36 hertz. There was a secondary frequency at about 2.7 hertz. And I couldn't get this to scale very nicely, but this peak is about 3 times as high as the secondary peak. This is data from the 4 different points along the tower height, all shown at once. So the blue is about 9 meters tall on the tower, then the green at 22, the red at 33, and the lighter blue at 49 meters tall. So you can see, as you expect, the higher you get on the tower, the more movement you get. The lighter blue has a much greater peak-to-peak displacement than the reflection points near the base, which have very little peak-to-peak displacement. Again, as you would expect, because it's all one tower, the bending action of the tower, the time of the data lines up perfectly. So that the vibrations happening at the exact same time. So if you did the Fourier transform on any of these points, you would get the same resonant frequencies. This just kind of illustrates that, again, we're able to look at multiple points along that tower height simultaneously. And this was just picking off 4. There was, probably a couple of dozen points we could have picked. So the IBIS system can perform well in measuring the displacements and associated resonant frequencies of the wind tower turbines. The displacement at a specific height was consistently proportional to the strain data acquired near the base of the tower. And that indicated that the tower displacement was really due to the bending of the steel as we expected. So a summary of IBIS-S applications: it's great for rapid bridge load test, has very great accuracy of 100th of a millimeter. You might need corner reflectors on some bridges, particularly concrete bridges. You can also do modal vibration measurements. You can monitor stay cables, and you can, from the monitoring, you can calculate natural frequencies and then move on to even tensions of the cables. We have done a large bridge in the US for stay cable monitoring. There's also applications to wind turbines and buildings. Again, you can measure those structures, get resonant frequencies very quickly and easily, and use that to further some structural analysis. And the keys for the technology are really the line of sight and speed of light technology. So you really have to be able to see the reflectors in order for that IBIS system to measure them. So with that, we'll turn it over to a question and answer period.
So I'm going to stop that and start our video. Let's see. Okay, we're live. You can come in, Pat. We're happy to answer any questions. Ryan, have we got any chat questions?
Yeah. The first question is could there be applications for machine vibrations?
I guess my answer to that is really large machines, yes.
Yeah, if it's a small machine sitting on a pad, it's probably better to do it with an accelerometer or a vibration measurement system. If it's a large, certainly a large machine that it's hard to access, then it could certainly work.
Yeah, thinking back, I one time did monitoring with seismic accelerometers on an ore crusher at a gold mine, and that was a large enough structure with columns and points that could have been measured. It does have one limit versus accelerometers. It is 1 degree of motion, where you could have a triaxial accelerometer for all 3 degrees of motion. So it works best when you're most concerned about either vertical or horizontal, like a building, or the towers would be horizontal motion. And of course, a bridge is normally vertical motion.
Have you used this system for longer term monitoring?
Yes, for landslides, because that's set up specifically in slope stability and rockfall monitoring and dams, things like that, because that tracks back and forth. It's set up with alarms and good control. And Pat and I will undoubtedly talk about that in the future. But the static, it tends to not be so much long-term monitoring. It could be.
Yeah, there is a static option for the IBIS-S to monitor bridges on a and usually that static is over the course of hours or maybe a day. The challenge is you can get drift in the signal due to changes in the atmosphere. So changes in the atmosphere can affect the radar speed through air, and you get drift in the signal. And so you have to be able to correct for that. So you really need a point in the field of view that you know or are willing to assume is not moving at all. And using that as a reference, then you can monitor the static movement of other things in that field of view.
Can the system rotate to do 360-degree monitoring?
Some of the new rockfall and mining applications by IDS can do that, but not the one for bridges and structures. It's going to have a field of view of, say, up to 70 degrees.
Yeah, and as Larry mentioned a minute ago, it's really a 1D system. So it's measuring displacement towards the system, and we have to assume that that displacement is in a single direction.
How are your points selected for a linear element like a bridge stay or cable?
Well, you don't go right at either end, obviously, and it tends to be like you would do in normal monitoring, maybe the third points of the cable.
Yeah, when on cables, if you're set up near a pier and you're shining up looking at those cables, you try to pick an angle to hit, and it's just kind of where the angle of the sensor, where that wave is going to primarily hit the cable, and you would like to angle it so that you're not at the nodal points of the cables.
But it does work over a length, and as you can see, it compared well with the accelerometers. If you're comparing to accelerometers, you try and point it at the accelerometer. But I guess the other comment there is you have to be, say, ideally 1.5 meters apart to separate the cables. You need that geometric separation to stand out. You don't want them all 0.75 meters apart. That's a little tight.
Right, and most cables are fanned out at least that far.
One other thing that you want to think about, and it's obvious, you pause, you have to see the cables. If you line them up so they're hidden behind others, you'll just see the first cable.
On the bridge from Manhattan, do you have measured natural frequencies before and after the torque stiffening system was added?
It's unknown to us. If anybody did, it was probably Columbia University. But I don't know if Dr. Smythe did that or not.
Was it included in the TRV paper?
No. My suspicion is they may have some of that data, but I'm personally not aware of it. The TRB paper was focused on how was it moving after the torque stiffening had been completed, which was a 9 to 10 year period.
If you were to use the system for monitoring a maglev track, is there any issues with electromagnetic interference?
Electrically, that hasn't been an issue before, and we've worked near some big power lines and trains and such.
Yeah, I don't think so, because we're looking at such a specific frequency range from 17.1 to 17.3 gigahertz.
Which is, of course, very high frequency.
But we'd have to think about that a little more.
I think, obviously, any electrical system, if you don't have it well shielded and grounded, but it is, could pick up electrical noise. But and it is in a metal box, so I think it's pretty shielded. One thing I didn't emphasize, but I mentioned it, is you can, with just a few simple screws, change the antennas to have different fields of view, going from plus or minus 15 degrees to up to 70 degrees, basically.
Right. We call them antennas. We often also call them waveguides, or horns, the little horns on the front that are guiding that wave.
Yeah, they're technically an air horn antenna.
You have a system for compensating for movement of the tripod with the sensor on it.
We always try and find a base that is not a problem that way. If that became an issue, technology is available in a slightly later version, it's the same otherwise, of a built-in accelerometer to remove the vibration effects. But of course, we recently did it over a pier with traffic, and it wasn't an issue when it was sitting on the deck on right over a pier.
At a pier, yeah. Yeah, we try to find a stiff spot. So if we're looking for vertical movement, we don't want to be the system moving vertically. If we can be decoupled from the structure, that's ideal. But a later version of the system does have a built-in Excel that you can correct from that data for.
Yeah, we've been using the system since 2010, and that was the main update to the structural monitoring, is to add an accelerometer.
Mm-hmm.
But of course, in the first place, you'd like to avoid that, even if you correct for it.
What's the approximate cost of the system?
Nominally $100,000 for the IBIS-S. But of course, I'll refer you to our neighbor, IDS-Geo Radar in Golden, to quote anything like that.
Could this system be used for seismic assessment for a large-scale shake table testing?
If you can mount the reflectors and say be back roughly 25 to 30 feet, and they have different distances that you can identify, yes. What do you think, Pat?
Yeah, it's hard to get data indoors. We've run it in our shop with reflectors, and we can usually pick off a reflector on a tripod, and we've moved it around and played with it that way. But there's a lot of clutter indoors, especially on our shop. It's, a lot of HVAC stuff, and there's just a lot of reflections indoors. So it can be hard indoors unless you got a really big space. Outdoors would be cleaner. And like Larry said, you want to be able to get far enough away that you can have a good view of those reflectors and have those reflectors spaced adequately apart.
But again, I think your main problem is going to be that you, doing shake table type work, might want triaxial responses. And this is uniaxial. You're making a decision, vertical or horizontal, basically.
Do you have a system for performing temperature, barometric pressure, any other weather corrections?
Just what's available on the web from these many weather stations.
Yeah, the IBIS-S system that runs the landslide monitoring, they have algorithms built into the program, IDS does, that correct for atmospheric changes, so that they can get around that problem when they're doing the landslide monitoring. And that's, they kind of pick off stable reflectors in their field of view that aren't moving, and there's a complex algorithm to correct for that. So that's all built into the IBIS-S system. For the IBIS-S, I don't know of any corrections that are easy to apply there.
It's generally so short term, it hasn't been a big issue.
Yeah, when we're looking at dynamic movement, as far as, you know, driving a truck across something or cable vibrations, we're not at all worried about that. It's more when you're trying to do a static application over the course of hours where that might come into play. And again, if you can find, if you have a point in the field of view that you know is fixed, then that's the best way to correct for it.
The last question is, for the wind turbine monitoring, is there a reason you didn't do monitoring while the turbine was spinning?
That was just the decision that was made at the time. I think they considered it a safer way to do it. They didn't want us kind of around doing things on the turbines when they were going, so it was done while they were shut down.
I think it could be done. You'll have some interference, obviously, if the blade is in your field of view when it does go by.
Yeah, again, you want to be on that downwind side of it, and I'm guessing that you'd have a lot more resonances created in the tower from the nacelle and the spinning of the blades. So it may be it's probably a more difficult study to do, and it wouldn't necessarily give you the true natural frequencies of the tower.
Okay. Well, Pat and I both want to thank everybody for attending it today. We will be sending out an email notifying you when it is posted up on the website. And if you had any questions, either one of us would be more than happy to talk to you about it. Hope it's useful to you on your projects, and hope everybody stays healthy and have a good day.
Thanks.